race to win wars and explore the stars, have created some of the most fantastic products ever designed, and we use them every day, unaware of their amazing origins. On Wicked Inventions. The computer, developed by World War II military boffins, but so simple even a child can use it. The flying disc, how a pie tin was transformed by a downed fighter pilot. Cutlery, how useful tools and weapons became an essential dining companion. We reveal the amazing science and manufacture behind these wicked inventions. Computers have become such an everyday fixture in our world that it's difficult to believe that just 50 years ago they were available to all but the richest corporations and had a calculating power of a fraction of even the simplest handheld mobile phone of today.
In essence, a computer as we know it today, what they essentially do under the bonnet is moving around ones and zeros. That's ultimately all that happens there. So by manipulating these ones and these zeros, you can do things like perform calculations. You can also use ones and zeros to represent information. But we can use it for very powerful means precisely because we can have lots of these ones and zeros and we can perform calculations very fast on them. That's all really that happens under the hood in a computer.
It's important though to understand that the word computer has a different popular meaning today than it would have done just over half a century ago. The word computer was first used in the 17th century and literally meant one who computes, or in other words, makes calculations. This then began being applied to mechanical machines as early as the end of the 19th century, but it was World War II that would see the word being applied to electronic machines beginning to resemble the ones we know today. Alan Turing and his team at the top-secret Bletchley Park were tasked with decoding the Germans' Enigma machine in order to give them the upper hand in the battle for the Atlantic Ocean against Hitler's U-boats.
He was probably the first person to realise that by setting up a machine would be able to combat or be able to produce something which would produce the results which would equal far many more brains, etc. But so in a way this was the origins of the first computer.
This then led to the development of the Colossus computer, the world's first programmable electronic computer. This could decipher even the most complex codes, keeping the Allies one step ahead of the Nazis.
And these then led to other inventions in the US during the end of the war, largely for the US Army to work out the ballistics so they could set their shells and artillery pieces more effectively. So these were the wartime origins of what we now know today as the computers.
Fast forward 50 years and open up any modern day games console or laptop and you will see microprocessors doing the job of the vacuum tube and electricity relay of old. Microprocessor technology has meant that credit card-sized computers can now be produced with a processing power thousands of times higher than those used in the war, and thousands of times cheaper too. This advancement is perfectly highlighted by the British-made Raspberry Pi, a single-board computer created with the intention of promoting the teaching of basic computer science in schools. What makes the Raspberry Pi computer so unique is its simplicity, and therefore the speed at which these credit card-sized computers can be produced. Astoundingly, one Raspberry Pi is produced every 7.5 seconds. The basic idea behind the production process is simple. Attach components to a printed circuit board, or PCB for short, with solder in order to create a mechanical and electrically conductive joints before being tested, packaged and shipped.
End to end it takes about 20 minutes to make a Raspberry Pi. That's starting with a bare PCB, going all the way through the two sides of pick and place, reflow soldering, wave soldering and then final test and pack.
The PCBs are mounted on a panel of 6 Raspberry Pis. This ensures minimal contact when handling and provides a waste edge around the boards that the machines can use to clamp the panel firmly into place. The bare laminate PCBs are screen printed with solder paste using a 100 micron stencil. When the stencil is removed, tiny prints of solder are left on the board. The machine performs an automated optical check immediately after the printing via a grayscale comparator. If any prints are missing, the paste can be easily removed and the PCB is reprinted. Now that the paste print has been verified, the boards are moved into an SMT mounting machine, where the surface mount components of the Pi are added. SMT stands for Surface Mount Technology and is a method for producing electronic circuits. Each of the tiny parts are in pockets on a reel of tape. A vacuum nozzle picks these parts and then spins around and places them onto the PCB at great speed. Once the parts have been placed, everything must be soldered into position. This is done in what is known as a reflow oven. This oven does exactly what it says on the tin and bakes the boards, which heats the tiny balls of solder in order to cause them to fuse to the component, the PCB, and each other. Another automatic optical inspection is then carried out, in which high-resolution cameras check the PCBs. The PCBs are then moved into another SMT line, where the process is repeated on the other side of the boards. After one more journey into the reflow oven and another optical inspection, it is now time for the boards to be moved on to the hand mounting line. Here, all the larger through-hole components are delicately but efficiently added by hand to the PCB of the Raspberry Pi. These components are things such as USB and Ethernet sockets. The boards are then passed through a wave soldering machine, where the components are permanently soldered to the board. This molten lava-like solder is heated and passed under the board in waves of metallic liquid. The height of the wave is carefully managed to ensure a quality joint. Skill and expert judgment are needed to get this exactly right. With this done, the Pis are fully assembled and ready to be manually inspected. This inspection takes roughly 30 seconds per board. The boards are then passed over to the test station, where the Pis are tested using in-house developed bespoke testing equipment.
So it takes less than a minute to test a Raspberry Pi, to go from a Raspberry Pi that's just come off the line to a Raspberry Pi that we've really beaten up and we know with good confidence that it's going to work at the user's house.
Here, the boards are broken out of the panel and placed onto the testing unit. Each station has 2 of these units, so that one can be used for loading and unloading, whilst the other is used to run the tests and also program the various setup codes, such as the model number and where it was made.
I think Raspberry Pi is a good example of where computers are going. Computers are becoming cheaper, computers are becoming smaller, computers are consuming less power. The interesting thing about Raspberry Pi 2, which we just launched and which is about 6 times as powerful as the original Raspberry Pi, is that it actually crosses over that line into being a usable general purpose PC. You could imagine buying one of these instead of a PC to be the machine that you have at home to surf the web or check email or watch videos on.
Every Raspberry Pi that passes the test is placed into an anti-static bag, along with customer-specific packaging. The finished computers are then sent off to be distributed to the growing millions of users across the globe. The big outdoors. Open spaces, contact with nature, socializing with other people. We've always loved to spend time in beaches, parks and woods, and outdoor games developed for our entertainment. One of those games has been hugely popular since the end of World War II and has given us hours of relentless fun. Inspired by a baking tool, designed in a prison cell, and enjoyed by millions of beach and park goers everywhere, this is the flying disc. This wonderful invention actually started life as an improvised plaything.
Students at Yale took the frisbees of the Frisbee Pie Company. They were being thrown around the campus and yelling "Frisbee" in order to have fun. It wasn't really commercialized, it was just simply the use of a tin.
In 1938, the commercialization of the flying disc began when a young American named Fred Morrison and his wife-to-be, Lucille, were offered 25 cents for a cake pan that they were throwing back and forth at a beach in Santa Monica, California. At the time, a cake pan would cost only 5 cents. The fact that people were willing to pay 25 cents for it got Fred Morrison to think of a business model for this baking tool. But World War II would be the catalyst for the development of the Frisbee. Morrison found himself piloting P-47s during the Allies' advance through Italy, but was shot down and became a prisoner of war. With time on his hands and his knowledge of aircraft aerodynamics, he could mull over the perfect form for his flying disc. On his return to the US, he developed several prototypes and started to manufacture the disc using the latest plastic materials.
He originally made it out of steel, and he incorporated the rim that we traditionally see in a Frisbee. He made it a steel reinforced rim, but it wasn't that effective. Basically, plastics became much more widely available and more useful for him. He took a butyl stearate product, polymerized it, and used it to make Frisbee. The nice thing about plastic is it was relatively cheap to make. It was also it was hard, and it had the flexibility that was needed to allow a Frisbee to work.
But how does the Frisbee actually work? A Frisbee is able to fly through the air as it uses the same aerodynamic principles as an aircraft wing to achieve lift, which is the force that allows the disc to fly. Because of the Frisbee's curved shape and rim, the airflow above it must travel at a higher speed than that underneath, thereby creating low pressure above and high pressure below the disc.
The air rushing over the top is a lower pressure, and it's actually sucked up by that. But it's also, because it's being sucked up, the air underneath, which is of a higher pressure, is pushing the Frisbee upwards.
But that is not the whole story. The secret to the Frisbee's success is the spinning action. The more the spin, the better it will fly. A Frisbee will fly best with the leading edge slightly raised in relation to the ground. This is called the angle of attack. Simply put, the greater the angle of attack, the greater the lift generated. But there is a trade-off. The greater the angle of attack, the more drag the object will create, and eventually it won't be able to fly. This is called a stall. The forces of drag, lift and gravity do not all act consistently on the centre of the Frisbee, which would mean a wobbly path in flight. Launching the disc with a large spin creates gyroscopic inertia, think of a child spinning top, which overcomes these inconsistent forces and stabilises the Frisbee in flight. The greater the spin, the more stable the disc, and the better it flies.
Gyroscopes are known for being stable when rotating fast, and a fastly rotating object is stable. So, when you rotate it fast as you spin it and throw it, that allows it to maintain a stable attitude, and so the air above it runs non-turbulent and can then fly a long distance. If you ever throw a Frisbee, you can tell that it's going to fail as it starts to lose that stability and starts to wobble a bit, and then it will drop to the ground fairly quickly.
In 1957, Morrison sold the rights for the flying disc to Wham-O, and in June of that year, the disc was renamed as Frisbee. It became hugely popular amongst university students and teenagers alike. Due to its popularity, official sporting Frisbee events started to pop up all over America, and Wham-O released the official Pro Frisbee model.
The Frisbee is actually a very popular item. It's cheap, it's easy to pack, and it's easy to throw around, and the game doesn't take much to set up. So you have many sports such as Ultimate Frisbee, where you play two teams against one another, trying to get the Frisbee into a touchdown area at the end, a bit like American football, except you can't tackle anyone. It's quite a competitive sport, it's played on world stages, and the benefit of it is you can do it with small groups of people and anyone can pretty much pick it up. You have Frisbee golf, where you can play it like a golf game and throw it towards a certain target, and there's par and there's all the similar rules to golf, as well as waterways causing you to have an out.
The flying disc or Frisbee is one of the most popular outdoor activities today. There is even a World Flying Disc Federation responsible for the organisation of the World Championships. In some countries, it is getting so popular that the sport is now recognised by the International Olympic Committee. So, it might be only a matter of time before the cake pan-inspired invention is an official part of the Olympic Games. Now that's a wicked invention. So, is the Frisbee the only unusually shaped, gyroscopically stable, fantastic flying projectile? Nope, and you can make one yourself out of rubbish. To begin, take an empty 2-litre plastic bottle, making sure it has perfectly straight sides. Next, we need to make a template to create 5 fins for our discarded flyer. Take a piece of paper large enough to wrap around the bottle, mark out the paper into 5 evenly spaced sections and fold them into a concertina. The fins need to be a series of nice smooth curves, so after making the centre point and a line 2 centimeters from the top of each section, sketch a curve so that when the paper unfolds, each curve seamlessly blends into the next. Now, carefully cut through all 5 sections to reveal a template of 5 fantastic fins. Wrap the template around the bottle and use a pen to mark the shape onto the plastic. Now take a pair of scissors and cut out your flyer to reveal your perfect fins and cut off the top of the bottle to complete the shape. Now the tricky part. Take off your template and go around the leading edge, gently pinching the plastic to create a 1 cm lip. Start slowly at first and then bend and press down once you have a definitive fold. Reinforce this lip with pieces of duct tape. You should now have a rigid, circular edge. Your recycled plastic bottle Frisbee Challenger is now ready, but will it work? Like a Frisbee throw, technique is all important, with the secret to add a nice spinning action on the throw. Boom, there you go. With a front profile that affords low air resistance and the spinning sides generating lift and gyroscopic stability in a similar way to the Frisbee, we really have taken recycling to a new level. Literally. Whether it be carving the Sunday roast in Britain or the turkey at Thanksgiving in the US, no decent home could be complete without cutlery. These simple, everyday implements have refined the art of dining. But did you know the war link between cutlery and the material it is made from?
Europe has certainly been one of the centres of cutlery and its predominance within society. Basically because the kind of food we eat warrants the use of cutlery. We've traditionally always eaten a lot of large pieces of whole meat, whole vegetables, whereas in other cultures where they chop it down, it's slightly finer. You think of things like how the meat is prepared in China where it's kind of broken down into fibres and stuff. This can be picked up quite easily with chopsticks. The European diet has always warranted the use of a knife and a fork and a spoon.
Usage of knives and spoons developed naturally over time to meet the needs of our everyday eating habits. The fork, however, didn't make an appearance until much later on.
In Northern Europe, the fork was seen as quite effeminate. And it wasn't until about the 18th or 19th century that the British especially started to adopt the fork. And whereas Sheffield was the centre of knife and cutlery production, Birmingham became the centre of flat press metal production, so things like spoons and forks became a lot more popular.
In 1912, with war in Europe not far away, the British government were researching better materials for the insides of their gun barrels. With the constant exposure to high temperatures when firing, their existing guns were experiencing problems with excessive erosion. A British inventor named Harry Brearley thought he had the answer, and in turn created a metal that would change the face of cutlery production. What Brearley did was to increase the amount of chromium in steel's composition. Unlike ordinary mild steel, the chromium steel mix performed a tightly bonded protective layer of chromium oxide on the surface that prevented oxygen in the atmosphere penetrating it and forming corrosion. And the material he developed? Stainless steel. Today we take cutlery for granted, along with some pretty strict rules that have developed about its usage.
In America, your fork will be in your left hand and your knife will be in your right hand. Once you've cut the meat with your knife, you'll place the knife away and then swap the fork to the right hand to eat. In Europe, it's the other way around. We keep our fork in our left hand, our knife in our right hand the whole way. When we put it down on the plate, that's the indication that we've finished eating. Whereas the Americans will put it at like a 10-to-2 angle.
This etiquette and the way we use cutlery has developed into its own unspoken language when it comes to eating in restaurants.
When restaurants became predominant, there needed to be some kind of code. You know, if you're an aristocrat sat in a salon restaurant in Paris, you don't want to speak to that waiter or that maitre d'. The way you position your knives and forks on the plate tells the waiter, I'm still eating, I'm not eating, take it away, or it was rubbish. So cutlery is kind of the unspoken language of the restaurant.
So, the next time you're out for a meal, take a long hard look at the spoon as well as the soup it's on. If it's stainless steel, then you have gun design to thank for its creation. Liberty Tabletop have been making cutlery in Sherrill, New York since 2005.
Sherrill, New York is pretty much in the geographic center of New York State. We try to source as much of our raw materials, supplies, packaging everything that we can in the United States. We require that our steel is melted here.
It's the only cutlery producer in North America, producing approximately 30,000 pieces of cutlery every week.
Depending on the complexity of the piece, it can take anywhere from 2 to 4 weeks to go from start to finish through the factory.
A 2,000-pound coil of stainless steel, that's around 900 kilograms, is hoisted onto a machine with a forklift truck. The flat steel sheet is fed into the blanking press, where the steel is cut into approximate shapes for the cutlery items.
And those blanks can actually be rolled and cut into different shapes, which would make forks and spoons of different outlines.
The blanking press takes 1 second to produce each blank, which can be made into spoons or forks. The blanks are sent to a rolling mill, where they are stretched out between 2 hardened steel rolls. The rolls have a specific precision ground profile, so that the bowls of the spoons and the tines of the forks will be thinner than the handles.
It's actually sort of similar process to rolling out pie dough. You roll it out so that you can cut out the cutout cookies, for example. So that's essentially what we do in that part of the process.
After the blanks pass through the rolls, they automatically fall into a punch press, where they are cut into an outline shape. Next, the pieces are put into an annealing furnace, which softens up the metal to enable further stamping and shaping. The furnace heats the metal to a temperature of 1,900 Fahrenheit, that's 1,000 degrees Celsius. Forks and spoons are now put through a coining press, where the patterns are stamped into the handles. They are then fed into another coining press, where the bowl of the spoon or the prongs of the fork are bent into the proper shape for use.
We bend the bowl or the fork tines. It's basically the piece looks just like a fork or spoon that you would use, except it's not polished.
All items are then polished in a series of shanking and edging machines. 3 shanking machines progressively grind and polish the shank area, the part of the cutlery where the bowl and handle meet. Then they go through an edging machine, where the handles are progressively ground and polished too. The final process is to buff the cutlery pieces to a mirror finish for a series of 9 separate stages of the machine.
We start with the bowl, move on to the handle, and then we go back to the bowl again, using 2 types of buffing compound. One is a roughing compound that smooths the surface, and then the final buffing compound, liquid paste, very fine grain. Then the piece comes out, I think it looks like a piece of jewelry.
The cutlery is then inspected and individually wrapped for delivery.
We have actually 100% inspection of all of our flatware. We look at it one at a time, and we wipe it by hand without using any harsh chemicals. We just wipe the compound off, put it in a bag, and it's ready to go to the customer.
Cutlery, truly a wicked invention. So there you have it, a dash through the hidden history, super science, and amazing manufacture of products that you use every day, but have never realised their amazing background. The computer, the flying disc, and cutlery, all wicked inventions.